Good afternoon, everyone, and early morning for some of my colleagues. My name is Yogendra, and I'm from Melbourne. And today we'll be joining my colleague Ian Cooper from UK. So I think we can start the webinar now. The agenda for today's webinar is actually we will be briefly touching the current trends in the EV market. That dominates the requirement and the future potential for this project. And then Ian will be taking us through the details of the charge project, which is basically an integration of the transport planning and electricity network planning. So that will be discussed in detail. And at the end, I will again, discuss how these learnings we can utilize in this region for the benefit of the end customers. So this is the agenda for today's webinar. Now let me just a couple of examples for EV market. Now the latest figures from UK market is actually in June 23. If we see the combined sale of fully electric vehicle and hybrid, it's almost crossing the 20% mark of the total sales. I mean, look, there was a time, so how quickly this is growing up. Australia, which has been a slow start, but in the first half last year, it was 1.8%, which had jumped 4 times, and it has become 7.4%. So, the graph is going up. In Singapore, there was a reporting from January to May, 13% sales of EVs. The globally, it is almost like 18%. And New Zealand market, is growing because there is a clean car discount, and the price of fully electric car models are coming down too. And we can see the combined of hybrid and battery is again will cross 10 in January and June 23 is more than 10% or 15%. So what in nutshell is this is all representing that EV market is growing exponentially, with or without the subsidies, but because of the battery prices are coming down, because of the EV prices are coming down, this market is actually taking off. Now, we are seeing that if actually people start doing and charging the car in the evening, even 50% people will do it, there will be a 25% surge in the peak demand. So this is the prediction, and this depends on many other factors: how we are charging, what is the incentives, what is the tariffs, how smart is the charging, all that kind of things. So basically, growing EV means growing number of EV chargers, both in-house, for the fleets outside, for the public, for the highways. So as the EV will grow, the private and public charges will grow in numbers. So this is the question, that how can we place the EV charger optimally where the capacity is, and also how can we charge EV when the network is not stressed. And this is the topic for today, that how can we optimize these two aspects, and this will lead to the increased utilization factor of the existing network assets, which will benefit to every electricity customer. I will now hand over to Ian.
So as Yogendra said, our objective for today is to show how data self-service tools can help DNSPs, network owners and operators enable this decarbonisation of transport, because it's coming. It's coming, and in many places it's here now already. So firstly, I'll talk through an introduction to the Charge project. Charge was all about public electric vehicle infrastructure. Where was it likely to be needed, and where was there grid capacity for it? If you can present these two pieces of information to people who are seeking to install chargers, then you have a treasure map of the best locations. For areas where there isn't available grid capacity, the project assessed smart charging flexible connections as a means of getting more EV chargers connected more quickly and at lower cost. Charge built on previous research and demonstration projects that have covered off-street electric vehicle charging. At EA Technology, we've been involved in projects in this space for about 12, 13 years, working with several different clients to identify and understand EV charging demand profiles, diversity factors, and customer behaviors. Charge sought to address the on-street, workplace, destination, and en route charging use cases. The project was a development and demonstration project bound within SP Energy Networks Merseyside and North Wales, or ManWeb, licence area, which has 1.5 million connected customers. Britain has had innovation funding mechanisms for electricity and gas utilities for nearly 20 years, stimulating innovation in the sector and helping utilities and the surrounding ecosystem of companies to look ahead and develop solutions to upcoming problems. It was targeting one of these funds that we, EA Technology, supported SP Energy Networks in developing the Charge projects back in 2018, then kicked off in 2019 through to completion in December last year. So let's look at the different main parts of the project and the different key people in the project team involved. So the main part for the first part of the work was PTV Group. They have modelled the entirety of the ManWeb license area covered by the project, identifying the EV requirements for each small geographic area. They're called LSOAs, or lower layer super output areas, in the UK. You can see from the graphic that PTV Group bring their transport planning systems and expertise into part one, method one of the project. And over the next couple of slides, you'll see how this comes together within this image. So Smarter Grid Solutions led the second part, method two of the project. They considered the potential flexibility from smart charging connections. They've developed a specification for determining whether customers can be offered a smart charging solution and conducted some virtual trials to assess how this might work in practice in this part of the project. And at EA Technology, we built ConnectMore as part three, or method three of Charge. This combines the transport model from PTV Group, the flexible connections from SGS, with data from SP Energy Networks for both the HV and the LV networks. We've taken this data from SP Energy Networks, processed it to develop the available network capacity, and present this in a customer-facing web portal that facilitates new connection requests. We're going to look at each of these parts in detail over the next part of the presentation. So firstly, the transport model. So as I said, the transport model for Charge was developed by PTV Group using their Vism software package. It's a tool for macroscopic simulation, modeling and strategy development, as it were a digital twin of the vehicle movements in the area that can be really helpful to predict future demand patterns given different scenarios. An EV infrastructure transport model is a powerful decision support tool that helps to quantify the requirements for infrastructure, and it's been used in transport planning for many years. And if you're trying to put together a holistic approach to plan future charging networks, it's very helpful. It should be noted that calibration of the model demand and the trip length patterns is important to help anticipate where and how much energy is required for charging. For the Charge project, we considered 4 charging use cases. We developed outputs from the model providing expected usage per LSOA for public destination, residential, and workplace charging. The charging in these locations varies from about 7 kilowatts for residential up to potentially 50 kilowatts for some destination locations. The en route data, the en route use case, is presented per road section. As you can see on the image on the right, the charging here was estimated to be between 50 and 350 kilowatts. We also considered 4 different model scenarios to provide some visibility of how the usage of charge points might change given different EV uptake and infrastructure deployment scenarios. So calculating the demand for public charging at a location considered 4 main factors. Some of these may seem obvious, but the number of EVs traveling to a location and the distance traveled provide the amount of energy consumed to get there and therefore required to return back. The number of EVs without home charging drives up the use of public charge points, as in most scenarios, it is cheaper in the UK to charge an EV at home on your domestic energy supply than anywhere else, if you have the choice. As an aside, there's currently a lot of press coverage in the UK highlighting the fact that domestic electricity is taxed, VAT, at 5%, while electricity from a public charger on street is taxed at 20%. As you can see, that seems not entirely fair. And there are a lot of players, a lot of parties within a country who need to line up and get coordinated to facilitate the rollout of electric vehicles in an equitable manner for all users. I hope that if you're watching this webinar online at a later date, this will have been resolved, particular nuance of the charging situation in the UK. But it's worth considering if you're engaging with your own government institutions to assess how this will be handled. I should probably also discuss the UK electricity network. UK has a 230 volt single phase or 400 volt 3-phase LV network with single phase services up to 100 amps being provided free by the network provider. This should cover 3 high demand assets in the home, such as electric cookers, heat pumps, EV chargers, which would cover most domestic scenarios. Some networks now are installing 3-phase cables into the premise as a standard for new properties or retrofits where there is sufficient space for the 3-phase termination to make this future-proof. I should also say the different data fields, the data types that are returned from the transport model are presented within the ConnectMore tool. The base figures are used to color the heat map on the grid geographic slide, and the rest of the information is within the sidebar on the right-hand side, which is downloadable and exportable from the tool if you want to interrogate this in more detail. So what did we learn from the transport model in the charge project? Presenting the results here for 2030, the biggest point that we saw was the huge potential range in electrical demand from EV charging, between 500 megawatt hours per day up to 3 gigawatt hours per day. In all cases, the biggest demand was expected from off-street residential charging, people with driveways. Notwithstanding my previous comment, that's often the most convenient for people. You don't have to go out of your way to charge up. We also noted that the presence of good EV infrastructure incentivized the EV uptake in a small way, increasing both home and public charging demand. But this analysis was carried out back in 2021, looking 9 years ahead. As you get nearer to the time, the particular scenario being followed will become clearer, allowing network planning to be made to cater for the demand increase with more confidence. If you want to look into the results in more detail, they are available online. Please follow the link on the slide or search for SP Energy Networks Charge Project. We'll now look at the second part, the second method of project, smart charging flexible connections, which were developed and led by Smarter Grid Solutions. The requirement for EV charge points is growing, as Yogendra said during the introduction, and this has increased from about 25,000 back in 2021, up to 44,408 now at the time of putting these slides together. And so probably by the end of 2023, it will have doubled in the UK over the last 2 years. And this growth is faster than new capacity is being added to the electricity networks. And it's likely to be faster at times, certainly once considered alongside the electrification of heat, then it's possible to build the network capacity. So I don't know if that matches your experience or what you're seeing or what you're forecasting where you are, but we'd love to hear what you're seeing and to help understand that better. So how do the utilities, how do the network operators handle this? The approach for other forms of demand or generation in the UK has been to use flexibility, or to flex the demand or generation up or down in response to the available capacity. This could be a permanent solution or a temporary one while reinforcement is planned or carried out or during outage situations. But effectively saying that most of the time you can get the capacity, you can do what you want, just not all of the time. So how could smart charging flexible connections be used? Could we apply this to electric vehicle charge points? And how might it be received by the people using those charge points? The original intention was to physically trial some smart charging charge points and to gather direct usage feedback. But having launched the project in 2019, then COVID happened. So the required level of customer engagement was no longer possible. And in its place, we carried out some virtual trials led by Smarter Grid Solutions with hardware in the loop testing, and we gained input from the EV driving public using surveys and online engagement. We considered 4 types of smart charging flexible connections. 2 of these are customer-led, 2 of these are network-led. First, the timed constrained connection schemes. So in this case, the connection agreement between the charge point operator and the network specifies a different amount of capacity at different times. So if it's in a residential area, it might allow a higher consumption overnight when most of the domestic load, such as heating and cooling, is off and the network utilization is lower. This is a very simple approach, allowing more capacity to be used at certain times and can be less flexible to changes over time should network circumstances change. It might also be appropriate to make allow a higher capacity during the middle of the day when solar generation is higher, for instance, or whatever the particular profile is that you're seeing typically on your networks. Second is a customer load managed schemes. These are already commonplace in the UK, and maybe where you are. If any of you with an EV have been to a busy en route charging station and have not been able to charge at full power, then you've probably experienced this. So this is certainly the case in the UK, where at some of these charging stations, there is insufficient grid capacity for all of the installed chargers to operate at their maximum output. So they are constrained by their charger control software to keep the aggregate level below the agreed threshold. Thirdly is locally managed constraint schemes. This is a network-led active control scheme where there is a single network constraint which may be local to or remote from the customer or the chargers. The network operator can then install some monitoring equipment at that location and manage the total demand against the constraint in near real time. Network operator equipment can send a control signal to the charge point controllers or otherwise provide a feedback loop to instruct them to turn down. This type of active network management has been in place in the UK for some years, but mainly for large renewable generation sites. It's quite quick, it's quite easy to set up as a secure communication method can be used, and it's not required to be integrated with the utilities core systems. It's not something that I know has been used for much smaller EV charging sites in anger at this time though. Fourth is centrally managed constraint schemes. In this situation, the network operator has an active network management or a distributed energy resource management system, an A&M or a DERMS or an ADMS or similar, which is connected together and able to control multiple devices out on their network. So multiple network constraints can then be observed and managed centrally, with control signals potentially being set to multiple demand and generation sites to avoid sections of the network being overloaded. It should be noted that none of these would stop the charge point operator reducing their charging rates in response to other utility service markets or the spot price in the electricity market. And I should also note that although we built the capability to advise customers of these smart charging flexible connection possibilities, SP Energy Networks have requested that we do not make this live in the ConnectMore tool because they've not carried out the other business change activities necessary to develop and deploy this as business as usual. So what did we learn from this approach? Well, as per previous methods, more detail is available in the learning reports on the SP Energy Networks Charge website. I particularly recommend the Public Charge Point Flexibility Insight report. We learned that smart charging connections offer utilities and customers a number of benefits. They enable utilities to provide new connections with quick and cost-effective alternative to network reinforcement prior to connection. You can get people on more quickly, which is what they want. We learned that customers with fixed geographic locations, such as workplaces, depots, leisure retail outputs, that wish to install a high volume of charge points will most likely be the early adopters of smart charging connection, because their location is constrained, so they have to make do with the network that's there or pay for whatever augmentation is required. We also learned that customers like simple solutions where they maintain control, specifically the customer load management approach, as it's something that they can adopt right now that enables them to get more charge points connected right away. And the functionality is becoming increasingly common in the charge point management software and easier to use. Customers also like timed connections for some use cases. For on-street residential charging, they're great because there's most likely to be a coincidence between the available capacity and the use of chargers. Also for fleets and depot charging fleets, they're really, really helpful where your vehicles are back in overnight, potentially in an industrial area where the overnight demand is much lower than the daytime. But in some other cases where there's less coincidence between the likely consumption from EVs and the other demand, these are less useful. I'm now going to describe the heat map and data layer functionality within the ConnectMore tool as part of method 3 within Charge. ConnectMore brings together the other elements of the Charge project and makes that information available both to SP Energy Networks and to their customers. So using detailed asset data provided by SP Energy Networks, we modeled the load on the network to a high degree of granularity, determining the highest load likely to be experienced by any asset on the network. This is a modeled, not a monitored approach, using typical demand profiles for connected customers and a statistical approach to the diversity of consumption found in typical networks. If you want to understand more about this approach, we're very happy to discuss it at another time. Combining this in the heat map with the EV charging demand from PTV Group allows users to determine their best locations for positioning charge points and connecting to the network. And this is live online. So please search for Charge SP Energy Networks Charge project or use the link on the slide. The videos in the next 2 slides are going to show you some of the functionality within ConnectMore. So looking first at the EV charging demand, the user has to set the type of charging requirements they want to look at, which of the use cases, and then define the scenario of interest by varying the uptake rate of EVs, charging point availability, and the time horizon of interest, which, based on agreement with our client, with SP Energy Networks, set to 5-year intervals from 2025 through to 2050. Most of this data, as you can see, is displayed by lower layer super output area, LSOA, for the whole of SP Energy Networks MemWeb license area, and selecting any of these areas will give you the forecast charging data associated with that LSOA for the scenario selected. All of the variables are shown in the right-hand toolbar are from that selected LSOA or road segment and can be exported out of the tool if required. So switching to the electricity network capacity section of the heat map, the user can decide whether they want to look at LV or HV capacity depending on the network configuration and the size of the potential EV charging connection being investigated. Selecting the LV network, you can see the assets displayed. There are a large number of secondary substations, approximately 12,500 in the MANWeb license area, and we can zoom in to display the individual cable and overhead line circuits. The electricity network assets are color-coded based on the capacity modeling results, built using data on the installed assets and the type, number, and location of connected customers. So a green asset has sufficient capacity remaining to add the requested new connection, leaving plenty of further capacity afterwards. An orange asset has capacity for the new connection, but has very limited spare capacity afterwards, and a red asset has insufficient capacity for the new connection. So using the example, which is a village near our office, near Chester in the UK, we can see that the main street circuit has no further capacity for even a 25 kVA connection, the lowest modeled for the heat map tool. But most of the surrounding circuits and all of the transformers have plenty of capacity. And then as you step up through the capacity request, you can see where there is no longer available capacity for that. But some capacity remains in the transformers, even at a reduced level. This approach is replicated for HV, just using a higher level of capacities. ConnectMore heatmap also includes some information about where SP Energy Networks plan to reinforce their network over the next regulatory price control period. This signposts to users the locations where there may not be capacity now, but there might be in the future. And this starts a different form of dialogue between the utility and their customer and enables different behavior, where a customer may hold off on connecting now because capacity may soon be available. This was particularly useful to customers in the UK as they had to pay for the upstream reinforcement when making a connection. However, as of April this year, the connections charging regulations in the UK have moved to a shallow charging model. And so this forward view of information is less useful because connecting demand customers will no longer pay for reinforcement of shared use assets. It's fair to say that there is a lot of regulatory change currently ongoing in the UK around data availability, around connections requirements, all around the model of presuming open data, providing information out to customers, to the public, where it is possible to do so, and trying to speed up the connections process. Because it's been identified in the UK that as with the EV uptake, the decarbonisation of transport more widely, the decarbonisation of heat, that actually the network operators and the networks and getting connected could be a blocker to that, to slow that down. And so there's a lot of focus, a lot of change being driven to help reduce the likelihood of that happen and overall accelerate decarbonisation. So it's a very interesting, very changeable time at the moment in the UK. So I'm now going to talk about the other side of ConnectMore, the cost estimator tool. So the video in this slide shows the user journey for someone seeking an estimated cost for a connection using the tool. It's embedded in SP Energy Networks website and has a disclaimer with all the appropriate legal information that this is an estimate and not an acceptable quote. And then they follow the process through. Identify the area where they're interested in connecting a load, confirming the total capacity required, setting the precise location for the new connection, and drawing the cable route and point of connection to the existing network. This enables the tool to provide a budgetary estimate for the connection, covering all the necessary work required, including network reinforcement if relevant. And I should say this isn't some sequences have been shortened to fit in the advert. This is a real-time screen recording of someone going through this process. Should the customer be optioneering to find the cheapest location or locations to put a connection in an area, they can start this process all over again and gain a range of options for pricing for different installation locations. Our UK clients have seen charge point installers seeking to install 4 or 5 charge points in a town, putting in potentially 50 to 100 connection applications to find the best prices. So in the UK, these are free. You don't get charged for connection applications at this location. So there is effectively no downside to these customers taking this approach. But there's a very clear downside to the utility, to the network, because there's a very high volume of requests that come through, which have to be responded to within a certain time frame. And the vast majority of the work is not going to materialize to anything. It's wasted effort. So providing this visibility out in the public domain is very useful for the utilities in the UK, because it reduces their workload, provides the information to customers, and they can optioneer, they can speculate themselves. And you're very welcome to have a look yourself at the tool online. If you put a location in the Merseyside or North Wales area, using potentially our office or Liverpool Football Club or some other well-known establishment in that space. So where do smart charging or flexible connections come into this process? The work from Smarter Grid Solutions is included in the cost estimator tool, and where the network does not have sufficient capacity for the planned connection, ConnectMore considers where a flexible connection can be offered. So looking at the example on the slide, the model showing the winter peak demand on the network is subtracted from the electricity network maximum capacity, or the ratings at the point of connection, and this gives the available capacity profile. I'm not going to give you the actual connection costs, but a connection application here requiring reinforcement would be quite expensive. But if the customer only needs 189 kVA, they can manage their demand to that level, the cost saving is very significant. The customer might manage their consumption to 189 kVA as a flat demand, or they could potentially have a timed or a profiled connection agreement allowing higher consumption overnight between 7 p.m. and 7 a.m. It is unlikely that a utility-led smart charging connection would be economically beneficial at this scale, but actually these customer-led solutions would be very viable to enable a customer to get a cheaper connection more quickly and to make the most of the available capacity. If you're using a dynamic operating envelope approach or similar, you could potentially push this as far as you can to get as much demand during the day to soak up your solar as possible, and in that way support your network to help overcome some of the other challenges that you have. Before we come to a view of what happened next, I'd like to share a few words from the License Director for ManWeb at SP Energy Networks, Liam O'Sullivan.
The Charge project has successfully delivered new and innovative ways for the UK to create a public charging infrastructure that both supports all EV drivers now and in the future. It's provided a vital insight into EV driving patterns and charge point demand over the next 25 years. It's also developed smart connection solutions that can maximize the use of existing network capacity and rapidly boost the number of public charge points. It's empowered stakeholders with a time-saving, self-service online tool that takes the complexity out of charge point location and provides instant connection quotes. We're incredibly proud of the Charge project's achievements and the way in which SP Energy Networks and its partners have worked together to produce a roadmap for the next phase of public charge point deployment. We hope that the new tools and methodologies we've developed will be used by the industry as a part of its business as usual activities going forward, whether in the deployment of flexible connections or in improving DNO's customer service.
So, as I said earlier, Charge officially finished at the end of December 2022 and is now completing a transition into business as usual. So what's happening here, I hope, will give you some insight as to where SP Energy Networks and the UK network operators in general are seeing value in the learning from projects such as Charge. So firstly, network operators are not tending to roll out transport models specifically, but they are making forecasts, and this forecast data available regarding multiple types of low carbon technology. So not just an expectation of electric vehicle uptake, but also heat pumps, solar, or other LCTs. This is produced as part of distribution future energy scenarios, and more is not just a data set, but is being published online through an interactive web portal. This data is useful for people who are doing modeling and analysis work, but is less specifically useful to EV charge point installers. But there is potentially a view that there are solutions available around EV charging demand, the transport modeling, that potentially companies who are looking to install the charge points can go and find that data themselves and do it separately. But the DNOs are not tending to roll this out. SP Energy Networks have not chosen to repeat the transport model development in charge for their other network license area, but they are continuing to make the data available for ManWeb that was developed in the Charge project. Secondly, the flexible and smart charging connections continue to be developed across the UK, with many networks adopting a flexibility-first approach to encourage the use of existing capacity rather than building new infrastructure where possible. This approach works for EV charging, especially where the customer can be put in control, keeping their demand at a point below a given threshold. Keep it simple, give them control, give them information. In many cases, it enables a much quicker, much cheaper connection, accelerating the uptake of electric vehicles. We should note that in many cases, this does require the network operator to put an end-to-end process in place. So not just the connection agreements, but the legal agreements, monitoring, management, enforcement arrangements. So as I said earlier, SP Energy Networks are not rolling smart charging connections specifically out to business as usual while they work through this, developing this other capability, but they intend to do this in the future. So using the heat maps and making the data available through GIS tools is very, very popular in the UK. We see most of the networks here having some system that presents the relevant data in this way. As I said before, there's regulatory pressure for utility data to be presumed open unless there is a reason for it to be withheld. With more and more data sets being made available all the time, SP Energy Networks have asked us to develop a network capacity heat map for their other network license area covering southern Scotland, and to continue to provide and update this for both areas over a multi-year period. We're also seeing a move towards self-service connections cost estimates in the UK. Currently, 86% of GB networks have these in place or in development, mostly using our technology. So we've currently have this self-service connections estimations live at LV for 3 clients in the UK across approximately 250,000 secondary substations, serving about half of GB. So working with our clients, we're continuing to innovate and push the capabilities of this technology at LV and HV, and for generation customers, for generating quotes, potentially customers could go through their whole connection process online, completely automatically in the future. So thank you for your time listening to me. I'd like to hand you back to Yogendra now, who is going to talk about how this might apply into the Asia Pacific region.
So look, I think the last part of the agenda was to see how some of these learnings we can use in this region. And we set ourselves the 4 targets. One was that give insights to where charge points might be most used under the transport planning. Now, this will definitely help if we know the traffic, if we know the consumer preferences, if we know where where people drive most, what are the clusters, where the heavy usages are there, what are the EV preferences. That will definitely help us to find the diversified EV demand profiles, and also the early detection of the clusters. So basically, if there is some data we can use from transport planning, and transport planning can say that these are the, assay one codes, or these are the, areas, geographic areas, and this is how the, the penetration will happen. So basically, like this will help our own electricity planning. And the second target we set ourselves is that provide visibility through electricity network capacity heat maps. Now, this helps two ways. One is that if we superimpose the transport planning needs with the electricity network available capacity, one, it gives the visibility to the network that where the demand is growing and the hotspots will be. And then the second is it gives the option for the EV charge point providers to find where the capacity is available, if that can be located on those, taking advantage of the available capacity. So basically, that means that visibility of that kind of electricity network capacity is important and has to be started from somewhere, and then it can be further improvised with when there's monitored data or there's more data is made available. Now, another objective, one of the objectives was that determine if flexible connections were viable. Now, look, this is a big social science issue because who will control, who will optimize from home, and how the DSO role is going to open up. So this definitely is a good option, and I can say in this region this has to be explored further. And the cost to connect through the self-serve tools, that is definitely on the agenda, saying because once we get the very high volume of connection inquiries, that is the tool to achieve the efficiencies, in terms of providing the, as Ian was saying, this through the self-serve connection tool or some other tools where the people, the large number of people can get the initial codes for the capacity where they want to connect. Now, I'm actually just quoting here the EV Council's latest report 2022, where it says that that some kind of data from the vehicle registration bodies should come to the network businesses, so that they can log this into the DER register and know where the charges are, where the EV clustering is happening. And it also says that DNSPs to improve the LV network visibility for internal use, so that that internal planning people can actually have a fair good idea of the demand requirement, the diversified EV plans, and show it to the public where the capacity constraints are or going to be. All right, so we are basically coming to the end of the webinar, and look, again, I want to say that this has been a great initiative where such a large number of customers and big networks. This was a big project in terms of superimposing the transport and network plan and the electricity grid planning, and which has actually given a direction for us that this is the way to optimize. And one of the questions for electricity network is definitely improving the utilization of existing network without going to spend too much money and burdening the customer. So there's already infrastructure. The question is how best we can use it, and these sort of initiatives which actually says that there is a possibility of optimizing, putting the charger where the capacity is and placing, planning the capacity where the demand is going to be. I mean, that is fantastic initiative, and it also leads to the visibility of the network, and ultimately it will lead to the hosting capacity and where the constraints are or going to be. So in that direction, I see this project has given very good start, and I'm actually going to thank everyone who attended this webinar, and I welcome everyone to contact me or Ian for any further questions or demo. So here we conclude this webinar. Thank you, everyone.
Cool. Thank you.